is Dr. Ajit Parwani. I would like to introduce Dr. Ajit Parwani. Dr. Ajitkumar Parwani is the Department Coordinator and Assistant Professor in the Department of Mechanical Engineering and Aerospace Engineering at Institute of Infrastructure Technology, Research and Management, IITRAM, Ahmedabad, India. He has completed his PhD at the IIT Delhi in 2013. He has over 15 years of teaching and research experience. His research interest includes heat transfer, inverse heat transfer, computational heat transfer, renewable energy, and IC engines. He has delivered several invited talk, keynote speeches, and presented research work in conferences and reputed institutes. He has published 26 papers in international journals and conferences. He has also filed an Indian patent titled Simultaneous Reduction of NOx and CO2 using exhaust gas recirculations and carbon capture. He has conducted several workshops, short-term training programs, and seminars. He has 2 ongoing research projects on inverse heat transfer funded by SERB DST, Government of India, and Institute of Plasma Research, that is IPR, Government of India. So thank you very much, Professor Ajit, being with us. I would like to hand over the mic to you and you can start your presentations. Thank you.
Yeah, thank you, Dr. Nitesh Shah and all the organizing team for inviting me and giving the opportunity to present my topic. Just to confirm, am I audible?
Yeah, you are audible.
Yes, okay. So, my topic of presentation is finite volume method in conduction and convection. So, what is this finite volume method and where it is applied? So, for the CFD, for the computational fluid dynamics, it is a method for discretizing the partial derivative equations. So, what is this computational fluid dynamics? The computational fluid dynamics is the science of predicting the fluid flow, heat and mass transfer, chemical reaction, and other phenomena. So, it is predicting these parameters by solving the equations for conservation of mass, energy, and momentum. Okay, so it is very well known to all of you that what is CFD. So I do not go much into this detail. We know that CFD can solve the fluid flow and heat transfer problems. So therefore, it can give the solution for the various variables like pressure, velocity, temperature, drag force, lift force, and all these. So in short, the CFD analysis complements the testing and experimentation by reducing the total effort and cost required for experimentation and data acquisition. And the major advantage of CFD is that there is no size and weight limitation. So you can use CFD or you can find out any parameter of for any size or any prototype of any size or any weight. So what will we do in the CFD? In the CFD, we are basically solving these equations. Okay, what are these equations? These equations are, this is the conservation of mass equation, which is also called as continuity equation. These are the 3 other conservation of momentum equations, also called as Navier-Stokes equations in x direction, y direction, and z direction. And this is the energy equation, right? So if we have a heat transfer problem or a fluid flow problem, so all these equations must be solved in order to get the variables values like velocity, the pressure or the temperature. Okay. So, so these equations are solved by means of computational techniques. Okay. So what are the other method that we can do to solve this problem? The other method that we can do to solve the problem is by analytical way. Okay, but analytical way is not always possible for every condition. Okay, so analytical solution is only possible for very simple situation. So let's take one example. So this is the example which is solved by analytical method. Okay, so what is this example? This example is there's a plane wall, right, of some thickness of length L. Okay, and the thickness is given to you, it is 0.2 meter. The thermal conductivity of the wall is also given to you. It is 1.2 watt per meter Kelvin. The area is given to you. And the temperature, the boundary conditions, the temperatures are given to you. So, this temperature is greater than this temperature, therefore the heat is transferred in this direction, the direction of the X. So our aim is to determine the temperature distribution at each and every point, right? So so you will see that this is a very easy problem, and because it's a conduction problem, I hope that I expect that all of you must know that what is conduction and convection problem. It's a solid domain, so there is no convection, there is only conduction. So it's a conduction problem. The wall is infinite in this direction, so therefore it's a one-dimensional problem. So therefore, out of these three equations, because there is no velocity term present, so therefore there is no mass equation or conservation of momentum equation is applicable to this problem. So only one equation which is applicable to find out the temperature is this. So in this equation, again there is no velocity, so therefore this term is not present. The problem is steady state, so therefore this term is also not there. Okay, there is no heat generation, so therefore this is also not there. There is no velocity, there is no fluid. It is a solid problem, so therefore there is no viscosity, so therefore this term is also not there. So, and again, it's a one-dimensional problem, so therefore the y direction or j direction is not there. So what remains? D square t by dx square is equal to 0. So therefore this is the only the governing equation which we need to solve. So now this equation can be solved computational or by analytical method, but this equation is very easily solved by analytically. How can we solve this equation? Just integrate this equation by twice. Okay, so if you will integrate it twice, you will get two constant of integration, and then applying the boundary conditions, you can solve this equation and you will get this relationship. So with this relationship, you can find out the temperature value at each and every point. Okay, so this is the beauty of this analytical method, that you can find out the temperature at each and every point you wish, right? Now you can solve this problem computationally, but for solving it computationally, you need to first define the grid points, and then you can solve this problem, this equation at these grid points only. So the variables are stored only at the grid point. So therefore, the computational solution you can do and you can solve it only at the grid points. But here you will get a closed form, the closed form of solution. So therefore, you can use this equation to find out a temperature at any point. But the analytical solution is, as I said, that it is not. You cannot find out the analytical solution if there is the convection problem, and if it's a transient problem, or if it is a multi-dimensional problem. So for these problems, you have to use the computational technique. So so what is the problem with the computational technique? Yes. Any question? Okay, so computational technique. So therefore, what is the problem with the computational technique? The problem with the computational technique is that the computer do not understand the partial derivative terms. So you will see the equations contain the partial derivative terms, right? So these partial derivative terms the computer do not recognize. So therefore, in order to solve it computationally, we need to replace these partial derivative terms with into some appropriate numerical form, and the process is called a discretization. Okay. So therefore, the analytical equation, if you want to solve through computer the equations we want to solve by computational technique, so we need to discretize the equation, or in other words, we need to convert those partial derivative terms into the numerical form. So there are various techniques are available, like finite difference, finite element, finite volume. There are other techniques are also there, but these are three basic techniques. And today I will only discuss the finite volume method. And I will discuss only for the heat conduction and heat convection problems. So what is the basic methodology for the finite volume method? The basic methodology for the finite volume method is, the first we need to divide the domain into n number of parts. So these parts could be a rectangular. You see, this is a domain, because we are solving the partial differential equation. So therefore, this partial differential equation representing for a very small part of the domain. So therefore, we need to divide the domain into n number of parts, and then we will apply those partial differential equation for each and every part. So the division could be a square, a rectangular, or some triangular elements like this. Okay, so or if it is a very simple case like a rectangular or square plate, then the division could be a square. The squares, the number of squares. So the first step is to divide the domain into n number of parts. and each part is called as control volume, right? Second step is to integrate the differential equation over the control volume. So therefore, then we need to apply the partial differential equation at each and every grid point. This is the grid point, and in each control volume there is a point. There is one point which is called as grid point. So we need to integrate the partial derivative equation at each grid point, and then after integration we need to evaluate the terms. So in order to evaluate the terms, we have to make certain assumptions, the profile assumption. What is that profile assumption? That I will tell you later on in my later slides. Then finally you will get, if there are n number of points, then you will have a n number of algebraic equation, right? Then you will solve all the algebraic equation simultaneously or by iterative method. Okay. So what is the actual procedure? I will tell you in with taking a very simple example in my later slide. So these are the steps. So before telling you the example, just let me define some more terms. The terms are, we need to discretize the domain into n number of parts. Each part is called as control volume. Okay, so these are the control volumes. And to each control volume, there is one node, that is what is called as computational node, right? On which this partial derivative equation is applied. Sometimes we will require the variables at the boundary points. Okay, so these are what are called as boundary nodes. For the conduction problem, the values of variables at these boundary nodes are available. Now, one thing you should always remember that the variables are only stored at these node points. So if the node points you fixed the node points, then it means that you can only obtain the solution at the node points only. You suppose the temperature, you will have it. You are finding out solution for temperature. Temperatures are only available at the node points, not in between. Okay, so if you want to find out temperature over here, then you have to define the grid point at this location. So wherever you want to find out the value of the variable, you define the node point at that location only. Then only you can find out the solution at that point. So this is a representation of a control volume in a finite volume method. So suppose this is the control volume, this is the computational node. The computational node is called as P node, and there are some neighboring nodes for this computational node. What are those neighboring nodes? On the east side, this is what is called as east node. On the west side is west node. On north, it is north N, and on the south, it is represented by the S. Similarly, in the three-dimensional problems, there is one more node on perpendicular to this sheet. So on that side it is bottom node, and on this side there is a top node. For the two-dimensional problem, there are only two nodes, two boundary nodes for this P. One is E and another one is W. There is no N, there is no S. Now this is the control volume, and for the two-dimensional problems, there are four control surfaces which constitute this control volume. So there are four control surfaces. This is the control surface E, this is control surface west, W, this is control surface N, this is control surface S. For the one-dimensional problem, there are only two control surfaces. There is only east control surface and the west control surface. The length of the control surface is in the y direction, it is given by delta y, and x direction is given as delta x. The distance between the two nodes in the y direction is delta y. In the north side, on the south side, it is delta ys. In east side, it is delta xe. In west side, it is delta xw. In this presentation, I will assume that all the length to be equal for convenience. Okay, so delta x, delta y, delta xe, delta xw, all the lengths I will assume to be equal. So now let's understand the finite volume method by taking this very simple example. So this is the example for the conduction problem, one-dimensional conduction problem with the heat generation term present. Okay, so this is the one-dimensional heat problem. Suppose there is a rod, a resistive rod in which the current is flowing. So if the current is flowing in the resistor, so therefore the heat is generated. So heat is also generating, and the heat is transferred as well as heat is generating. So this is the governing equation. The governing equation is, it's a one-dimensional problem, so there is only one variable. It's a conduction problem, so there is no velocity terms present. There is no I mean, only transient term is also not there because we are assuming a steady state situation. So therefore, I'm only considering the conduction term in one direction and the heat condition term. So now, how will I convert this equation to a numerical form, or in other words, how will I discretize this equation? By using finite volume method. So in order to discretize this equation by finite volume method, the first step is to discretize the domain first. It means that divide the domain into n number of gate points or n number of control volume. So the one control volume is shown to you here. The control volume for the P is shown. So in this control volume P, you will see it's a one-dimensional problem. So there are only two surfaces. One is east surface and the one is west surface. And the two nodes, the two neighboring nodes for this P are shown, one on the east side and one on the west side. And then the corresponding lengths are also given. So this is the first step, divide the domain into n number of parts. Now apply this partial derivative equation to each node and then convert into the suitable numerical form. Okay, so that the computer can recognize that equation. That equation is called a discretized equation. So in other words, discretizing this equation at each control node, at each computational node, or at each gate point. So first of all, I will discretize this equation at the node P. So how will I discretize this equation at the node P? By using finite volume method. The second step is to integrate this equation over this control volume. So the control volume is having two surfaces, east surface and the west surface. So integrate this equation from east to west. So integrating this term from east to west, integrating this term from east to west. So integrating this equation from east to west. Okay. So now if we will integrate this term, so what will we get? We will get k dt by dx at east minus k dt by dx at west. Plus this integration I will tell you I will discuss later on. So now focus on these terms. Now here you will see k dt by dx at the east face and k dt by dx at the west face. I already told you that the variables are stored only at the computational nodes. So we have the temperature values at P, we have the temperature value at the east, we have the temperature value at the west. We don't have the temperature values at this point, at the east surface or at the west surface. So how will you evaluate this? How will you convert this derivative term into the numerical form? So in order to convert this derivative term into a numerical form, we have to make some assumption. The assumption is the temperature profile assumption. We are solving the equation for the temperature, but here we will make the temperature profile assumption. It is up to you that you will choose any temperature profile. You will assume any temperature profile. You can assume like the temperature in each control volume will be the same. So in the control volume of the waste, the temperature is suppose TW. Okay, in the control volume of P, suppose the temperature is constant, which is TP. In the control volume of E, suppose the temperature is constant, it is TE. So if you will assume such profile for the temperature, and now in order to determine the temperature gradient at the east surface and temperature gradient at the west surface, you cannot determine temperature gradient at the east surface and the west surface if you will assume this profile. Okay, so you cannot determine. Why you cannot determine? You will see at each surface there are two values for the temperature. One is this, other one is this. So the temperature gradient at this surface is indefinite. So therefore, you cannot assume this type of profile. So what is the other profile assumption? You can make the assumption like a linear profile assumption. So if you will make the linear profile assumption, you can easily find out the gradient at this point. So what is the gradient at the surface now? The gradient at the surface now by this linear profile assumption is that this TE minus TP upon the distance. Similarly, this TP minus TW upon the distance. So dt by dx at E, if I assume the linear profile assumption, so I will get TE minus TP upon delta x, and for this W, it is TP minus TW upon delta x. So so by making this linear profile assumption, we can convert this partial derivative terms into the appropriate numerical terms. Right, so therefore the equation, this partial derivative equation is replaced by this equation. So therefore this equation is called as discretized equation. Now this discretized equation is obtained by assumption of the piecewise linear profile. It is up to you. You can choose any other profile. If you want to choose the quadratic profile, you can do this. There is no harm. You can choose any profile. Okay. But if you will choose this step type of profile, you do not get the value of the the value of the gradient at this surface. So this is the easiest profile that you can choose. We have chosen, and by assumption of this linear profile, we can discretize this equation into this form. Now this term is the source term, which is a heat generation term. Normally the heat generation term are given in the per unit volume, right? For example, in a domain, this is the heat generation, and this is the heat which is generated per unit volume. So for this control, if the heat generation per unit volume is given as is represented by S bar. So for this control volume, for this control volume, the total heat generated is S bar into delta X. The length of this control volume is delta X, so it is S bar into delta X. So this is integrated. This source term is integrated, and it is also given as S bar into delta X. So it is not always. Sometimes the heat generation is depending upon the temperature. So heat generation is a function of the temperature. Then in that case, what will you do? That I will discuss later on. But here, for a very simple case, you could assume that the source term is a constant term. It is a constant, and heat generation is given as per unit volume. Okay, so heat generation is constant, and it is given as S bar per unit volume. So this is the discretized equation. Now, in the finite volume method, there is a particular form of representing this discretized equation. The form that the finite volume method uses is this: APTP is equal to AET plus AWTW plus B. So we have to convert this equation into the standard form of the finite volume method. Okay, so in this form, we need to convert the equation into this form. So in order to convert this equation into that form, what will we do? We will take the TP terms on one side and take other terms on the other side. So you will see the TP terms, I am taking all the TP terms on this side and TE, TW and other terms on this side. So if we will do like this, then these are the coefficients of for the control volume, for this method, for this finite volume method. This is coefficient for the point P, this is coefficient for the point E, and this is coefficient for the point W. So if you will compare these two equations, the coefficient for the point E or AE comes equal to KE by delta XE. So AE comes equal to KE by delta XE. Coefficient of W comes equal to KW by delta XW. Coefficient of AP is KE by delta XE, which is equal to AE, and KW by delta XW which is equal to AW. So AP is equal to AE plus AW. B is equal to this source term S bar delta X. Okay, so this is the the standard form of the finite volume method. So this is the discretized equation which is obtained by applying the finite volume method, and this is a standard form. So we will discretize in this format. So in general, if it is a two-dimensional problem, or it's a three-dimensional problem, then in general the discretized equation is written in this form. That is APTP is equal to AE summation of neighboring points of A neighboring T neighboring points plus B. Okay, suppose it's a two-dimensional problem, then some more terms will get added, like AET plus AWTW plus ANTN plus ASTS. If it is three-dimensional problem, then two more terms will get added, like ATTT and ABTB, that is top point and the bottom point. So like this, we can in the general form we can write this finite volume discretization equation in this way: APTP is equal to summation of A and B, T and B plus B. So this is the method, this is the procedure. Now what are some comments on this procedure? So the comments are that here we have used the simplest profile assumption, but you can use any interpolation function that is also okay, that is also valid. The other thing that is important is that it is not necessary that you will use the same profile for all quantities. What does it mean? Here this KE and KW, right? This KE and KW, right? Suppose the conductivity is also varying with this domain. Okay, there is a variation of conductivity in this domain. So if I use the the profile assumption for the temperature in order to find out the value of dt by dx at east by by assuming the profile as a linear function, so shall I use the same profile for finding out the value of k at the east surface, because k at e is not available. Okay, for k at e we have to convert into either in p or in e terms. Okay, because the variables are only stored at the node points, not on in between the two gate points. So in order to find out the value of ke, shall I use the same profile? I mean, shall I assume the same profile as I assumed for the temperature? So it's not necessary. You can use any profile for the conductivity. Similarly, if the source function is also having some some variation, like source is also a function of temperature. So for calculating the value of the gradient of the temperature, I use the linear profile, right? So for calculating the source term, shall I use the same profile? So shall I use the same linear profile? So it is also not necessary. You can use any profile for calculating the temperature for the source term. So it means that for the same variable, that is for the temperature term, you can use any profile you want. For calculating the gradient, you can use one profile. For the calculating the source term, you can use other profile. So it is not at all necessary to use the same profile for the temperature for calculating the gradient and for calculating the source term. Similarly, it is also not necessary to to use the same profile function for calculating the thermal conductivity value. So therefore, it is important to understand that we need not to use the same profile for all quantities. Okay, even for a given variable, the same profile assumption need not be for all the terms in the equation. So therefore, even for the same variable, you have the different profile function, and for the other variables, I mean, you can use any profile function for any variable. But whatever you will use or whatever you will assume, the solution that you will get, it should be realistic solution. Okay, so what is realistic solution? What is unrealistic solution? Suppose if it's a conduction problem, suppose there is the temperature on this side is higher than the temperature on this side. Suppose temperature on this side is 200 and temperature on this side is 50. And if you will find out the value of temperature at the point P, and temperature at the point P comes equal to 500. Okay, so this is what it comes to unrealistic solution. Why it is unrealistic solution? Because here the temperature is 200, here temperature is 50. So how the temperature will come for the point P is 500? So it is very unrealistic. Okay, or the temperature at P should not be equal to 10 degrees centigrade. Why it is not 10? Because here the value of the temperature, if it is a non-heat generation term is there, it's only a conduction term is present, and temperature at the P could not go below this 50 degree value or below or above this 200 degree value. Okay, so these are the very unrealistic solution. So the temperature, if the temperature of at one end is this and the temperature at the other end is this, then the temperature in between could not be the more than this value. So it is very unrealistic solution. So therefore temperature in between could not go below this value, which is also very unrealistic. This is the approximate. If you will get a solution like this, so it is valid solution. It is approximate solution, but physically realistic solution. So when the solution will go unrealistic, so solution will go unrealistic if it do not pass some rules. So what are those rules? I will define those rules in the later slides. So solution could not be unrealistic. I hope that this is clear to everyone up to this point. Now, treatment of the source term. What is this source term? What is this treatment of a source term? Now, as I said, that this source could also be a function of temperature. It is not always that source is a constant value. Okay, if it is a constant value, then I can use S is equal to S bar delta S. There is no issue in it. But if it is not a constant value, it is having some function of temperature, right? Then what should be the value of S bar? Then if it's a function of temperature, then S bar contains the value of some constant value, and then a function, some coefficient of this temperature, which is on which it depends. So this source it can be written in this form: Sc plus Sp Tp, where Sc is the constant part of this source and Sp is the coefficient of the variable part of this source. Okay, then our the discretization equation formulation will change little bit. How it will change? You will see. Then A comes if I as in place of S bar, if I write SC plus SPTP, then what will change? There will be changes in AP term and there will be changes in the B term. So what is this? AP will be now this SP term is comes in the AP equation, which is SP delta X and B is equal to SC delta X. So these are the little bit changes. The source is function of the temperature. So it is not necessarily the source is always a function of the linear. I mean, it's a linear function of temperature. It could be the function of the square of the temperature. It could be function of the cube of the temperature. When it is there, then we have to change into the linear form. How can we change into linear form? That I will discuss later on, because the linear form is very easy to handle. So therefore, if the source is a function of higher power of the temperature, then we need to convert the source term into the proper linear form. How will we do this? That I will discuss later on. So now let's discuss that when the solution will be unrealistic. When it comes here unrealistic. So there are some rules that should be followed if we want the solution do not become unrealistic. So what are those rules? So in the finite volume method, there are 4 rules that you should always check that your discretization equation should validate those rules. So what are those rules? The first rule is the consistency at the control volume phase. What does it mean? It means that you have the freedom of choosing any profile function for, as I said that for temperature you can choose any profile function, but that profile function should be, consistent. If it is not consistent, then you cannot get the consistency at the control volume phase. What does it mean? It means that suppose there is a flux value at the, suppose there are 2 control volumes. Just see this diagram. So suppose there are 2 control volumes. One is P control volume and one control volume for the E. Now this E surface is common to the control volume of P and E, right? So for this control volume of P, this is the E surface, and for the control volume of E, this E surface is also there. So this E surface is common to the adjacent control volume. So it means that at this surface, the flux, the flux that passes from P to E should be, the flux that passed from the P, it should be received by, the same flux should be received by the E. That is, the flux at this surface should have a single value, should not have a double value. That means there should be consistent flux at the surface E, because E is common to both the control volumes. Okay. So when it will become different? It will become different if we will choose the different profile function for the temperature for the 2 control volumes. Suppose for the E control volume, if I choose the profile function like this, okay, and for the P control volume, if I choose the profile function like this, okay. So now at the surface E, now you will see there are 2 temperature values, and therefore there are 2 temperature gradients. This temperature gradient is this, and the temperature gradient is this. So therefore there are 2 temperature gradients. So if there are 2 temperature gradients, it means what? It means that the flux that passes from P to E will not be equal to the flux that comes out to the E. So the continuity equation will not be satisfied, or the energy equation will not get satisfied. So therefore, in order to satisfy the conservation of energy principle, the flux at the common surface should be the same. So in order to have the flux at the common surface should be the same, you have to choose a consistent profile for the for calculating the gradients for every control volume. This is the first rule. The second rule is positive coefficients. Okay, so as I discussed that for the finite volume method, the equation comes like this. So these are the coefficients are AP, AE, AW, AN, AS. So according to second rule, the coefficient should be positive. Now, why the coefficient should be positive? I mean, the coefficient should have the same sign. It should be either positive or should be negative. So it must have the same sign. So why this rule? Now, the applicability of this rule can be understood by by considering one example, like suppose if this is a conduction domain, and suppose if this is a point P. So suppose if the temperature of the point P is Tp, the temperature of the point W is Tw, and temperature of the point E is T. So if I suppose if I heat this point P, the temperature of this point P will increase. So because of the conduction problem, the temperature of the point E should also increase, and temperature of the point W should also increase. So the temperature of the point P, the information of the disturbance at the point P should reach to the neighboring points also. In the same way, suppose the temperature at the point P increases, then the temperature of the point W and temperature at point E should also increase. If the temperature of the point P decreases, then temperature at the point E and temperature at the point W should also decrease. So therefore, in order to have this type of relation, all the coefficients should be the positive, or all the coefficients should be negative. If it is not, then what will happen? Then if the temperature over here increases, and if the coefficient, one of the coefficient is negative, then the temperature, then you will reach a solution, you will come to the unrealistic solution. The unrealistic solution is such that if the temperature of the point P increases, then temperature of point W may decrease. So therefore, in order to do not have an unrealistic solution, then all the coefficients should have the same sign. So this is the second rule, that the coefficient, that the discretized equation should be such that all the coefficients must have the same sign. Okay, so we have assumed the linear profile function. So with the linear profile function, we reach the discretized equation like this, right? So both the rules get satisfied with this discretized equation. How it's satisfied? Because we have assumed the linear profile function for all the node points. So therefore, the consistency has been satisfied, and you will see all the AP, AE, and AW all are positive, because conductivity is positive, this is positive, this, so AP, AE, and AW all comes positive. So both the rules are satisfied, the discretized equation that we had obtained. Okay, so these two rules are satisfied. Now what is the third rule? The third rule says that if the source term is a function of temperature, okay, if the source term is a function of temperature, then the coefficient AP can become negative. Okay, so how it becomes negative? You will see, if the source term is a function of temperature, then AP is written as AE plus AW minus of SP delta X. So suppose SP becomes, if the coefficient of this SP is greater than AE plus AW, then what will happen? AP will be negative. So therefore, our second rule will get violated. So in order to have this positive coefficients, this SP will not be a negative. SP should not be a positive value. If SP becomes positive, then AP could become negative. So therefore, SP, you have to choose the source function so that the SP will always be a negative value. Right. So if the SP is always a negative value, then AP, AE, and W will be the, and the rule 2 will always be the valid. So this SP should always be a negative value. So is it in our hand to have the SP value to be negative? Yes, we have to discretize in this way. If SP is positive, suppose, if S is depending on the this temperature, the positive coefficient of temperature, then we have to make something, we have to do something that SP value we will take as a negative. Okay, so what will we do, that I will discuss later on. Okay, but in most of the practical situation, SP is mainly negative, so there is nothing to do. You have to do nothing, and because in most of the situation, SP is mostly negative. For example, suppose in a resistance heater. Okay, suppose if SP is not negative, then what will happen? If you are heating, okay, if the heating is in the heating, there is a source. Okay, so if there is a source, and if the source is positive, depending on the positive value of temperature, then what will happen? The temperature will increase, the source will increase. And if the source will increase, we know that the temperature will increase. So you cannot get a stable kind of situation. Why you do not get a stable kind of situation? Because if the temperature will increase, the source will increase, and because source is a function of temperature, then again the temperature increase, the source will increase, and source will increase, the temperature will increase. So it means that you do not get a stable kind of situation. For getting a stable kind of situation, SP should be negative. Okay, so in the practical case, SP is always negative, but in some cases, if it is not negative, then we have to make it negative. How will you make it negative? That is the I will tell you later on. Right. So this is the rule number 3. So the final rule is that sum of neighboring coefficients. So it means that the coefficient of the computational node should be equal to the coefficient of the neighboring nodes. So this is the rule number 4. So why does this rule? This is the rule because this is suppose this is our the differential equation, the two-dimensional conduction equation, and this is the discretized form of this equation. Okay, so this is a differential equation, and we are discretizing it into this form. APTP is equal to summation of n, because there is no source term present here, so therefore there is no p term here. So now, if this is a discretized equation and this is the equivalent. This is a discretized equation which is equivalent to this partial derivative differential equation, or which is the representation of the this analytical equation. This is a numerical equation and this is an analytical equation. So if both these equations are the same, then if T satisfies this equation and T plus C satisfies this equation, then T and T plus C should satisfy this equation also. What does it mean? Suppose if this is the equation and here the T is satisfying. Okay, so if T is satisfying, and if I will increase the value of T, say by plus C value, some arbitrary constant value T plus C. So T plus C value also satisfies this equation. If T is satisfying, and then T plus C is also satisfying. So in this equation, T and T plus C both are satisfying. So in this equation, T and T plus C should also satisfy. If it is not satisfying, then what does it mean? It means that this is not the true representation of this equation. If this discretized equation is a true representation of this equation, then whatever this equation has the features, this equation should also have the same feature. So this equation has a feature like T and T plus C satisfy this equation, then this equation should also have the same feature like T and T plus C should also satisfy this equation. So in order to reflect this feature into this rule should get satisfied. If this rule not satisfied, then this feature is it will not be there. Then this is the not true representation of this equation. This can be understood by one example. You will see this is the example which I have written over here. Suppose this is the problem of one-dimensional heat conduction with the source term. Okay, this is a numerical. This is a partial derivative form of equation, and this is the equivalent discretized equation, or the numerical form of the equation. This is the partial derivative, and this is the numerical. So both the equations are the same. If both the equations are same, it means that whatever the this will have, whatever the features of this, the same features should satisfy this equation. Okay. Now suppose if TE is equal to 200. Okay, if I write this, if T is 200, TW is 100, and suppose if B is equal to, there is no source term, so if B is equal to 0. So if T is equal to 200 and TW is equal to 200 and A is equal to 2 and AW is equal to 3. So what should be the value of TP comes? The TP value will come equal to 160. Okay, and AP is equal to 5 and suppose SC is equal to, so P is equal to 100. So now suppose if this if I increase if I increase the temperature by the value of 20. Okay, if I increase the value by the value of 20, so if I make TE is equal to 220 and if I make TW 120, okay, then what will this equation will get satisfied? I mean, if I putting the values, all values here, so the equation will be satisfied. Okay, now this equation will be satisfied only if AP is equal to AE plus AW, that is phi is equal to 2 plus 3. But suppose if AP is not equal to AE plus AW, if AP has some other value, and then now writing the putting the values over here, you will see the equation will be satisfied in this case. But if I increase the value by 20, okay, if I increase the value by 20, then you will find that the equation will not get satisfied. So it means that if AP is equal to AE plus AW, then only the equation will be this is the true representation of this equation only if AP is the summation equal to summation of AN. So all these rules must be validated if we do not want to have an unrealistic solution. So if the unrealistic solution, if we do not want the unrealistic solution, all the 4 rules must get validated by the discretized equation. So now these are the rules and these are the discretized equation. Now we use this discretized equation at each and every node, and then we have a n number of algebraic equations, and these n number of algebraic equations can be solved by using the Gauss-Seidel method. So what is this Gauss-Seidel method? It is the iterative method. It can be solved by the simultaneous solution by the simultaneous method also, but it can also be solved by using some iterative method like Gauss-Seidel method. What is this Gauss-Seidel method? In the Gauss-Seidel method, first what we will do, we will we have the n number of equations. Suppose we have the 8 grid points in a domain. We have made the 8 grid points in a domain, where 1 point in the 8 point are the boundary points, and normally these boundary points values are given to you. Then we have to make the equation for the the remaining grid points like 2, 3, 4, 5, 6, 7. So we have with the help of this finite volume method, we form the equations 2, 3, 4, 5, 6, 7. Right. So these are the equations that we will get. So what is this Gauss-Seidel iterative method? This Gauss-Seidel iterative method, in order to find out the value of temperature at the 2-point, temperature at the 3-point, temperature at the 4-point, temperature at the 5-point, we need to solve all these equations. So how will we do this? So first step is to assume any temperature values at all the grid points. Suppose I will assume 300 temperature value at the grid points, all the grid points. So assuming the temperature value, and then find out the value of T2 first. Okay, so putting the value of T1 as 300, T3 is equal to T4, T5, T6, whatever. I mean, whatever the variables in this equation has. This equation has only 2 variables, T1 and T3. So putting the values of temperature in this equation, and then you will get the value of T2, right? And then in the next equation, you will put the what the value of T2 you will get. You will put over here, and for the remaining variables, you will put the value as 300, the initial value. You will get the value of T3, right? So in this way, you will get all the values T2, T3, T4, T5, T6, T7. Then finally, you will check that the value that you will get now and the value in the previous iteration. Okay, so in the previous iteration, it means that our previous case was 300 for T2, and now with this, I will get say 500. Then the absolute difference of these two is 200. So our error is 200. So this 200 is a very large value. So therefore, again you have to go to this step again. Then T1, T3, T4, whatever you will get from this iteration, you will put the values and then find the new value of the T2. And this new value of T2 and the previous value of T2, if both the values difference may change with a small value, then it means that is the solution has been reached. So with n number of iterations, you will get the true solution. So if there is any question, I mean, I have told you many things. I don't know. I mean, if there is any question, you can ask, because this is the I'm taking a class at my institute for the PhD students for this computational methods, and up to this point there are maybe 5 to 6 classes will be completed with up to this point. But I have for this in this presentation, I have only in 1 hour I have completed this up to this point. So if you have any problem, you can ask, or if you don't have, I will proceed.
Sir, I suggest we can take questions at the end of this session.
Okay.
Yeah. Thank you, sir.
So, source term linearization. What is this? As I said, that sometimes the source is not a linear function of temperature. It could be the square, or it could be cube, or it could be more than that. Okay, and if it is there, then the discretization procedure will be very difficult. Okay, So in order to in order to facilitate our discretization procedure, discretization procedure, we need to, if the source term is having a power of temperature, then we need to linearize this source term. How will we do linearize the source term? We will do linearize the source term by this equation. The equation is S star plus ds. So the new value of the source is actually this, but we have to linearize it. So how will we do linearize? We will linearize by S star plus ds by dt star tp minus tp star. Now what is this star? Star means that we will take the value of the source from the previous values, from the previous iteration value. So what does it mean? Okay, I will tell you what does it mean, but first of all let me write down the star values. So what are the star values? So this is S star. So S star means that the variable in S is what? The temperature. So put T is equal to T star. So S star is equal to 4 minus 5 T star cube. So S is equal to 4 minus 5 T star cube. ds by dt. Now differentiate this equation and put the value of temperature as a star multiplied by Tp minus Tp star. So if you do this, you will get this expression. Okay. Now, what does this star values of temperature represent? The star value of its temperature will represent the temperature value that we will have obtained from the previous iteration. So, what does it mean? It means that these values are known to us. These values are not a variable now. The variable are only Tp, right? This Tp star is known to us, so it comes in the SC term. So, because we have to linearize this equation in SC plus SPTP. Okay, we have to linearize this equation in the form of SC plus SPTP, where we are finding the value of SC and finding the value of SP. SC is what? The constant term, and SP is what? The variable term. Variable at the point P. Okay, so this star values will comes in the constant term, and this value is in the SP term. So SP is SPTP, so it means that SP is equal to minus of this 15 TP star. So in this way, we have linearize this non-linear equation in this way. So what does this TP star means? TP star means, like we have solved this Gauss-Seidel method. So in this Gauss-Seidel method, if we are going to the iteration and then we are checking this, so what is the previous value of the temperature? Like the previous value of the temperature is this. It is known to us. Okay, this previous value is known to us. So if it is known to us, so therefore we have put into this constant source term. So SC plus SPTP. Now let's take second example. Now this is again a linear equation. There is no issue into it, so we do not need to linearize it. But what is the problem with this equation? The problem is that the source is now a positive function of temperature. It depends on the positive coefficient, and this positive coefficient will, becomes our fourth rule becomes invalid. Our second rule will becomes invalid. Why it becomes invalid? Because AP is equal to AE plus AW minus SPTP. If SP is positive, then this value will have a effect of like AP could become negative. So therefore, in order to satisfy that rule, we have to convert this equation into some other form. So how will we convert this equation into this other form? Suppose if we take SC is equal to 3 and SP is equal to 7, then this is not acceptable because it makes SP as a positive, and you will get the unrealistic solution of the equations. Okay, unrealistic solution. So in order to avoid that unrealistic solution, what will we do? We will take all these things into a constant SC value, 3 plus 7 TP star, and put SP is equal to 0. If we will do this, then SP is equal to 0, then our AE, AW, AP, ANS, all these are positive. So our rule will not get violated. If the equation is say S is equal to 5 minus 4 TP, so it is it is a normal equation and we have nothing to do into it. We just put SC is equal to 5 and SP is equal to minus of 4. SP is minus, so there is no issue into it. So this is how will we do the linearization of the source term. Okay. Similarly, we can, here I have not mentioned how can we address this conductivity Ke or Kw. So Ke and Kw, we are normally, if suppose conductivity, however, in most of the cases, the thermal conductivity is constant for most of the practical applications.
Excuse me, sir. Your screen is not visible.
Sorry?
Your screen is not visible. I think
I can't hear.
your screen.
Oh, screen is not visible? Okay. Is it visible now?
Yes. Now it is visible.
Sorry for the interruption. Where it becomes invisible? I don't know.
Just 2 minutes.
2 minutes before. Okay.
Okay.
Right. So yes. Okay. Where I was. Source term linearization. It happens. Yeah. I was telling the conductivity. Yes. So how will I address this conductivity? Ke. Suppose if Ke is, most of the practical situation, the conductivity is constant. Suppose if the material is defined, say iron or some other material, if it is a a homogeneous material, then there is no issue. The conductivity is constant, and then what is the value of Ke, and what the same value is Kp is the same value as Ke. So Ke you can take Kp or Ke if it is constant. But if it is not constant, then what will you do? Okay, so if it is not constant, then we will have to take the harmonic mean of the conductive values of the P and E. Okay, this is the normal practice that conductivity, if it is not constant, then at the control surface the conductivity value is assumed to be the harmonic mean of the conductivity value of the two gate points. Okay, so we can take K at this control surface is equal to Kp multiplied by Ke upon Kp plus Ke, like this. There is a harmonic mean of the two conductivities of the two gate points, adjacent gate points. This is you will address the conductivity. There is, however, there is theory behind it. I am not going into that theory, but there is theory behind it. Why will we take the harmonic mean? Why don't we take the arithmetic mean? So there is theory, and I will not discuss this theory now. Okay, and okay, so that's all for the conduction. So now for the convection problems, there are other things also there in the conduction that I'm skipping because of the time constraint. So this is what is conduction. Now coming to the convection problem. So what is the difference between the conduction and the convection? In the convection problem is if there is any fluid involved, then that is a conductor. Now the domain is the fluid which is flowing. Okay. So if it's a fluid, then our energy equation have one more term. This is the conduction term, and one more term is added in the energy equation, which is having the velocity term. Right. So now how to discretize this equation? If I want to solve a fluid flow problem, if I want to solve a convection problem, so how will I discretize this equation? And what is the difference? This type of equation is called as the parabolic form of equation, parabolic form of partial differential equation, and the equation that we had used in the previous conduction case, like this. So this equation is the elliptic form of equation. Now what is the elliptic form, what is parabolic form, what is hyperbolic form? Again, there is a theory of the partial differential equation which I am not going here. So this is what is elliptic form of equation. But what does elliptic form of equation means? That elliptic form of equation means that the solution should be such that it is called as a marching problem. Okay, this elliptic form of equation, it is called as a marching problem. So how will we solve this marching problem? How will I discretize this elliptic form, or how will I solve this marching problem? So in order to solve this, there are various schemes are available, and the schemes that are there, it is based on the discretization of this marching variable. This velocity is the marching variable. So the schemes that are available is to how to discretize this term. Okay. So the first scheme is called a central difference scheme. In the short form, it is written as CDS. Right. I'm starting with a simple problem, one-dimensional heat convection problem. So this is a one-dimensional domain, which I have three node points. One node is P, one node is E, one node is W, and this is the control volume. These are the control surfaces E and W. So now our find volume methods. The second step of find volume method is to integrate this equation from east surface to west surface. So if I integrate this from east to west, if I integrate this from east to west, so what I will get rho u e minus rho u w, and integration of this is similar. I mean, this is conduction. Here it is written as lambda, a general variable for the conduction. So k. This phi is the general variable. So it could be temperature T. So this is k dt by dx at the east, k dt by dx at the west, and this is density U T E minus density U W. If I integrate this from east to west, I will get this. If I integrate this from east to west, I will get this. So now here I make some assumption. The assumption that I make, because here there are two variables. One variable is the velocity, and another variable is the temperature, or any other variable like phi. So how can I solve the equation with the two variables? Okay. In this simplest case, if I assume that the velocity is known to me, I mean how the velocity is known to me, this velocity can be solved by solving the momentum and the continuity equation. Okay, so there are three equations that I have described in my first slide. One is the continuity, one is the momentum, and third one is the energy equation. Right, the energy equation is the equation for the temperature, and the continuity and the momentum equation are the equation for the velocity. Okay, so this velocity term, we can get this velocity term by discretizing the momentum and the continuity equation. This continuity equation and momentum equation is discretized. There are different methods, and there is again a large theory that I will not discuss in this class, in this presentation. But suppose if I discretize those continuity and momentum equation, and if I solve those discretized equations to computational by the use of the computer, and then finally I will get the velocity field. Okay, if I will get the velocity field, then I will get this equation. Now this equation has now only one variable, so I assume that there is only one variable to solve in this equation, which is the value of phi. So how will I solve the value of the phi? This is the energy equation. I have integrated, and then this I will get. So now there are various schemes to solve this equation. The first scheme which I am discussing now, it is a central difference scheme. So in this central difference scheme, the profile function that has been assumed to solve this term, to this convection term, is the linear profile. So if I assume the linear profile, then the temperature at the E, I can write temperature at the E is equal to temperature at this E computational node and temperature at this P computational node. So this is TE plus TP upon 2. If it's a linear function, then I can write TE, or the phi E, phi is the variable which is equivalent to temperature. So this phi E, I can write phi E is equal to phi E plus phi P by 2. Why I have written phi E is equal to phi P plus phi by 2? Because I assumed the temperature as a linear function for this case. Okay. So if I assume the linear function, then I can use phi. I can write phi is equal to half of phi E plus phi P. Okay. So remember, the value of temperature is not known here. The value of the temperature is not known at the control surface. So therefore, we have to convert this temperature value at this surface into the node points. So we have converted this phi E into phi E plus phi P as by assuming some linear profile for the temperature. Then I can write T E plus Tp by 2 as phi. Similarly, phi W, if I assume some linear function of temperature over here, then I can write phi W is equal to half of phi P plus phi W. So putting this phi is equal to half of phi plus phi p, and putting this phi w is equal to half of phi p plus phi w here, I will get this. And this equation is discretized in the same way because it is a conduction term. So this conduction term, I already have described this. So it is discretized in the same way like we did in the conduction problem. So this is, we have described like that. So this is the final discretized equation of this differential equation. So this differential equation is this, and this is a discretized equation. So now our standard form of the finite volume method is what? The standard form of finite volume is AP phi p is equal to AE phi plus AW phi W. Right? So therefore we need to rearrange this equation into this form. So you will do the rearranging, that is take the phi p terms on one side and other terms on the other side. So what you will get? You will get AE value is equal to this, AW value is equal to this, AP value is equal to this, AE plus AW. Now what is F? Suppose rho u, if I assume this rho u, because it is known to me, so rho u, if I assume rho is equal to F, and gamma by d or k by delta x, if I write k by delta x as d, so F and d, so therefore AE, AP, AEW all are given in terms of F and D terms. So what is the problem of this CDS scheme? This is a CDS scheme and this is a discretization equation by we are getting from this CDS scheme. So what is the problem that you will see? The problem that you will see from this discretization is that this AE could become negative if the value of FE comes greater than twice of DE. If the value of FE comes greater than twice of DE, then the value of AE could become negative. If AE becomes negative, then our second rule will get violated. And if our second rule will get violated, it means that we will get some unrealistic solution. Okay, so let's examine this. Suppose if there is a convection problem, this is a one-dimensional convection domain, and suppose the value of D means k by delta x. So value of D at E and D at W is k by delta x over here and k by delta x over here is equal to 1. And value of F, what is F? F is equal to rho u. So value of F at E and value of F at W, it is equal to 4. So obviously F is greater than 2. So it means that it should give the unrealistic solution according to the our rules. So you will see how now let's examine this. Now suppose the temperature at the point W is say 100 and temperature at the point E is 200. Okay, temperature at the point E is W is 100 and temperature at the point E is 200. So if it is this, if these are the values, that is phi is equal to 200, phi w is equal to 100, dw is equal to 1, fe, few is equal to 4, then what is the value of phi p? The value of phi p will, if I use the central difference scheme, the value of phi p is equal to ae phi plus aw phi w upon ap. What is the value of ae? The value of, ae, aw and phi and phi w. Phi w value is 200 and 100, and what is the value of AE and AW? Value of AE is equal to D minus FE by 2, and what is the value of AW? AW is equal to DW plus FW by 2. So putting this value, you will get the value of phi p, and you will be amazed that you will get the value of phi p is equal to 50. So what does it mean? It means that phi is equal to 200, phi w is equal to 100, and you will get the value of phi p is equal to 50. So which is unrealistic, okay, which is not possible because phi p should not, because there is no heat generation term here. We have solved this equation without heat generation. Okay, so if there is no heat generation, so it means that the temperature should not go, beyond the smaller value. The smaller value is 100, so the temperature in between should not go beyond 100. Okay, so it is a unrealistic option. Now let's examine another way. What is the other way? Suppose now Fe is equal to 100 and Fw is equal to phi w is equal to 200. If phi w is equal to 200 and phi is equal to 100, then what is the value of phi p? So if you will solve this by using dE, dW is equal to 1, Fe, Fw is equal to 4. If you solve, then you will get phi p is equal to 250. So again, phi p comes greater than 200. So therefore, it means that the CDS scheme will give you the unrealistic result if this value comes greater than twice of d. If phi value is greater than twice of d, so it means that you will have some unrealistic result. Now, what does this phi value represent? The phi value represents the velocity. And what this d represent? D represent means diffusion. So it means that if the velocity is higher, if the convection term is higher, if this is dominating term, if the convection term is dominating, then the diffusion term. Okay, so if this convection term is dominating, then a diffusing term, and then if you are using central difference scheme, then you will get unrealistic result. So therefore, if the convection is high, then you cannot use or you do not use the central difference scheme. If you will use, you will get the unrealistic result. So if we do not use this scheme, then what are the other scheme? The other scheme is called as upwind scheme. So this second scheme is upwind scheme. So what is this? So in this scheme, we will choose the upwind variable. Okay, what does it mean? It means that if I'm in order to find the value of phi, or in order to find the value of phi w, that is temperature at this point. So if the temperature is at this point, if the velocity is in this direction, okay, if the velocity is in positive direction, and if the temperature is at this point, so phi at this point, I will use only the upwind variable, that is phi, I will choose only phi p. So I will take phi is equal to phi p, upwind value. Suppose if the f is less than 0, it means that if the velocity value over here is less than 0, it means that it is in the opposite direction. Suppose if it is in this direction. So if it is in this direction, then the upwind variable for this at this point is this, because the velocity is in this direction. So if f is greater than 0, then phi I will choose equal to phi. So according to upwind scheme, I will use, depending upon the direction of the velocity, I will choose the value of the variable at the control surface. So in this way, what should be the value of phi w? If the velocity is this, if the velocity is this, then the value of phi w, if the velocity is this, then the value of the phi w is phi w, phi capital W. And the velocity is in this direction, in the negative direction, then what is the value of phi w I will take? The value of phi w I will take is equal to phi p. So with this arrangement, okay, with this arrangement, I will get a discretized equation like this. Okay, so now what is this discretized equation? Now we will see this. There is some operator comes here. What is this operator? This operator is the selection operator. So because here we have to make the selection depending upon the condition. Okay, so if the velocity is in this direction, then I will choose the upwind variable. If the velocity is in this direction, then I will choose this variable. Okay, so we need to choose one variable depending upon the direction of the velocity. If the direction of velocity is positive, then this A comes equal to D only. Then it means that the selection operator will choose the maximum of the two values. If Fe is positive, then the maximum two value is 0. So it means that A is equal to D, and AW is equal to DW plus FW, and AP is equal to this. Fe minus Fw is always 0, because this Fe minus Fw means what? Rho u at east minus rho u at W. So according to continuity equation, the continuity equation is rho u e minus rho u W is equal to 0. So this is always 0. So there is no issue into it. So if Fe is positive, then A is equal to D, AW is equal to DW plus FW, and AP is equal to AE plus AW. If Fe is negative, then A is equal to DE plus Fe, because if Fe is negative, then this value comes greater than this. So AE is equal to DE plus Fe. AW is equal to DW only, because then when it becomes negative, then this becomes negative. So the higher value between these two is 0. So therefore AW becomes equal to DW, and AP is equal to AW. So with this, you will see that all the coefficient, the second rule is, it is not violated. So AP, AE, AW all comes positive. Okay, so AP, AE, and AW all comes positive. You do not have violate any rule. So this is what is the upwind scheme. Okay. So now this upwind scheme, definitely it will not give you the unrealistic solution. The central difference scheme will give you the unrealistic solution. Why it is given unrealistic solution? Because when Fe becomes greater than twice of De, then A becomes negative, or second rule will get violated. If second rule becomes violated, then you will get the unrealistic solution. But here you do not have, in this discretization method, you do not have any such difficulty. All the coefficients are positive, and this discretization scheme will follow all the rules. But now the question is whether this upwind scheme will give the true solution or not. It will give the approximate solution, because whatever the solution that you will get out of the computational technique, all are the approximate solution. Why it is approximate solution? Because here we have chosen, like the profile function we have chosen, we have assumed, and the other things that we have used into it. So therefore you will do not have an exact solution. You have some kind of a approximate solution. You do not get exact solution. So will upwind scheme will give you the realistic solution, that is true, but will it give the realistic solution or not? This is what we want to check. So how will we check this? We can check by using this. Okay, just a minute. Yeah, there is a exact solution is also available. I have skipped that slide into from here. Okay, so there is one exact solution is available, and exact solution is this. Okay. Now what is this? I mean, if the differential equation is this, now for this differential equation you can easily find the analytical solution also by doing integration, and you will get the analytical solution. So if you will get the analytical solution that will come if you will solve mathematically this equation, the analytical solution is in the form of the exponential terms like this. Okay, so this exponential terms, analytical solution will come in the exponential, and if you will compare the upwind scheme and this CDS scheme with this exact solution, you will get some idea that what upwind scheme will give you the true solution or not. Okay, I think that I have such graph. Just let me check. Yeah, here it is. Okay, so you will see there are other schemes also shown in this graph, but I just have to confine my attention on the upwind scheme and the central difference scheme. Okay, so suppose this is our domain. Okay, this is our domain, and here it is. This is the P domain, and here it is. I mean, this is the P control volume. This is the E control volume. This is the W control volume. And suppose the value of phi E and phi W is 1 and 0 respectively. Suppose here it is P, then here E is suppose 0 and W is suppose 1. So phi W is 1 and phi E is 0. So what should be the value of P? Okay, or what is the value of temperature in this domain? If the temperature at the west point is 1 and temperature at the east point is 0, then what is the value of temperature at 1? So by mathematical solution, by mathematical solution of that governing equation, the exact solution which is of exponential nature. So this dark line that you will see, this is the exact solution. Okay, this dark line that you will see, this is the exact solution. The temperature at any point at any point in the domain, you will get the temperature at any point in the domain with sorry, this is a variation of the Packlet number. Now what is this Packlet number? So sorry, any question?
No, sir. Please carry on. I think it was just some disturbance.
Okay. So you will see this is the exact solution, and this is the central. This solution comes from the central difference scheme. Okay. Now you will see the central difference scheme is giving the good solution up to the Packlet number value lies between this and this. Now what is this Packlet number value? Packlet number is actually ratio of the F by D. Okay, this is the Packlet number value. I'll not mention anywhere, but yeah, here F by D. So if you will find the ratio f by d. That ratio is called as Packlet number. Okay, that is the rho u upon gamma by delta x. So this is what is called as Packlet number. So that if you see the f by d is having a small value, so the Packlet number is very small. That is, the velocity is very small. F by d is equal to p. Okay, this p is equal to f by d. So if f is very small, then Packlet number is very small. If the velocity is very small, then Packlet number is very small. If the f is very small, then with the central difference scheme, you will get the exact solution. There is no issue into it. But as the Packlet number value increases, and if it increases more than twice of d, then you will have an unrealistic solution. You will see the solution goes beyond this value. Solution goes beyond this value. Okay, solution will go above this 1.11, and solution will go less than 0. So which is unrealistic. Okay, so central difference scheme will fail if the value of Packlet number is very high. Packlet number means the value of f is very high compared to the d. Whereas the upwind scheme will always have a value. You will see the upwind scheme is always having a value which is close to the exact curve. It is not exactly, but it is not giving the exact value, but it is very close to the exact curve. Okay, so it is giving the realistic value, but still it is having some deficiency. Okay, still it is having some deficiency. So what is that deficiency? The deficiency is that this upwind scheme that we are using, the variable that we are choosing at this surface, we are using only the upwind variable, and this is only if the value of velocity is very high. And if you will see the exact solution, first of all, analyze this exact solution. What is this exact solution will tell you? The exact solution will tell you that with a very high Packlet number value, either in positive direction and in negative direction, the exact solution will approach the upwind point. Like you will see at the Packlet number value greater than this, or Packlet number value greater than this, then this exact solution, you will see here the exact solution will give you the value of 1. Here the exact solution will giving the value of 0. So it means what? If the Packlet number is negative, I mean if this is if the velocity is this, then p is exactly equal to, I mean phi w is exactly equal to, if the value of velocity is this, phi w is exactly equal to phi w. And if the velocity value is in this direction, then phi w is exactly equal to phi p. If it is very high value, the high value means the velocity value, the Packlet number value goes beyond this value. But the upwind scheme will fail to detect this. Why upwind scheme will fail to detect this? When we have taken the the upwind variable for discretizing the convection term, it is true that we have used the upwind variable for discretizing this convection term, but for discretizing this diffusion term, that d phi by dx, d phi by dx at east phase and d phi by dx at west phase, we have used the linear profile. We do not have used the the upwind variable, or the upwind variable, like we have for this for the discretization of this convective term we have used the upwind variable, but for the discretization of this term, the diffusion term, we do not have chosen the upwind variable. We have used our conventional discretization, like we have used the linear profile. Okay, so we have done like this. So in order to evaluate this derivative term, because of this, the error will occurs in this upwind scheme. That this is a difference because of the wrongly use of the profile function for evaluating the differential term. Okay, so therefore the upwind scheme is not a real. It will give the approximate solution, but it will not give you the true solution. So what will be the true solution? The true solution is we have other schemes. I don't know how much time do I have, but I will discuss this last scheme, which is the exponential scheme. Then I will leave this presentation. So this exponential scheme is based on the exact solution. Okay, so our exact solution, we know that we have the exact solution is this. So why don't we derive the discretized equation based on this exact solution? So exact solution, we know that the exact solution is is of the form of the exponential nature. So this is the exact solution. So if we will use this into our discretization scheme, then we will have a scheme. The scheme is called as exponential scheme. Now, how will we use this exact solution into our discretization scheme? For this, suppose our differential equation is what? Our differential equation is this: d by dx of rho u phi is equal to d by dx of gamma d phi by dx. So what I will do, I will make this arrange this equation by taking this term on this side. So this equation becomes d by dx of rho u phi minus of d by dx of gamma d phi by dx. Then d by dx I will take common, so it will become rho u phi minus gamma d phi by dx. So this variable I will use this rho u phi minus gamma d phi by dx as one variable, because I am assuming the profile function as exponential for both, for convection as well as conduction term. For upwind scheme, the problem was that I have used the for this variable I have used the upwind value of the variable, and for this variable I discretize, like I have assumed the profile function, and then I will take the value of this gradient. But here in the exponential scheme, now I am combining these two variables into one variable. The one variable is called as j, and now this j is equal to rho u phi minus gamma d phi by dx. So now our equation becomes dj by dx, and if I integrate this, then I will get je minus jw. So now I have only one variable, and now in order to evaluate the j at this surface, and I have only one profile assumption, and the profile assumption is the exponential profile assumption, and that profile assumption comes from this exact solution, where this is the Patel number. Patel number is equal to f by d. What is f? F is equal to rho u, and d is equal to gamma by L. So if you will use this, then if you will put phi is equal to, by arranging these terms and putting phi is equal to this, and then find out the value of d phi by dx, and then putting over here, then you will get je and jw comes equal to this. Okay, if je jw comes equal to this, then putting over here you will get the equation like this. Okay, so AP phi p, AE phi, and AE phi, AE AW, and so this is what is called as exponential scheme, and this exponential scheme is based on the exact solution. Therefore, it is the it is very much approximate. It is very much approximate to the exact solution. Okay. But still there are some deficiencies in this exponential scheme. What are the deficiencies? That here it is there are exponential term. Okay, this exponential term is very, it's a very computationally expensive term. So therefore, we do not, this term is computationally expensive. Therefore, if you have 100 or 1000 or 1 lakh of grid points, and if you will use this exponential scheme, so that that will involve large amount of time to solve the problem. So therefore, there are other schemes have been developed, like hybrid scheme, power law scheme, and the other schemes are also. So there are many schemes, but I'm now, finishing my presentation here. If you want to learn more, there is a book which is called as Patel, Numerical Fluid Flow and Heat Transfer. The book name title is Numerical Fluid Flow and Heat Transfer. The book is totally based on the finite volume method for the conduction convection problems, and you can refer that book. So with this, I'm ending my presentation here. If you have any questions, you can ask.
Thank you so much, sir, for your presentation. One question I would like to ask you.
Yes, sir.
As we are aware that whenever going with this numerical approach,
Right.
The other part with which we go ahead is computational part. Whenever we want to feed these value to our computer.
Right.
Okay. So, as per you, which of the solver we should go for? Maybe if we go for such heat transfer problems.
Yeah, I have shown you one problem. Probably you missed that problem, like Gauss-Seidel method. I told you, right? So suppose this is the equation, the standard form of the finite volume equation, and you have n number of gate points, right? So if you have n number of gate points, and then you can write with this equation, you will have at each gate point at each gate point you will have I mean, you can write the equations for at each gate point like this by using this standard form of equation, and then by Gauss-Seidel method you can solve and you can find out the value of temperatures at each point by computational. Okay, with the help of a computer program by MATLAB or by any other platform that you will choose, C, C++ or whatever.
Okay, sir.
I had the program. I can show the program also, but I don't know whether I have time or not.
Yes, sir.
Sorry?
We
I
have
have a MATLAB program with me. A simple problem, a two-dimensional problem is there, and I have one MATLAB problem. I mean, one MATLAB program is already with me, because I'm working on inverse heat transfer method. So that program is extended to the inverse heat transfer. But for the inverse heat transfer problem, we have to first solve the direct problem. I mean, we have to solve this first, and then we will go to the inverse. So that MATLAB program is available to me. I can show you if you will permit.
Yes, sir. Yes.
Okay.
We can go for extra 10 minutes if you.
Okay. Then I will search where it is. Just please stay for a few minutes. I will just search.
Yes, sir. Yes. Meanwhile, I'll convey. I just want to convey this to all the participants. If you have any queries, you can ask it now, or if you want to ask it later, you can mail the same to me, and I can get in touch with our expert and will let you know the reply. And even you can ask your queries right away.
Is my screen visible?
Yes, sir. Yes.
Yeah. So it's a MATLAB program actually, and this is a program with a coil tube. I mean, it's in an angular direction. Okay, I have just discussed in the in the Cartesian coordinates, but this program is prepared in the angular coordinates. Okay, so just I will give you some flavor of it. I mean, first of all, I have to define the theta here, and in the case of the Cartesian coordinate, we first define what are the grid points in the x direction or in the y direction, like that. Here I define in the grid points in the radial direction as 25. The grid points in the angular direction is 25. Then you will divide. Then you find out the value of dr and d theta like this. So similarly, you can find the value of dx and dy in the Cartesian coordinates. And then you will assume with the Gauss-Seidel iteration method, then you will assume that the temperature value for initial gas has some value like this. The other constant like conduction, density, velocity, whatever it is. So you will use you can first define all these variables. So the problem, I mean the solution that will start, it will start from here, right? So this is the small error value. So the loop will get terminated if the error value comes less than this value, right? And now depending upon the boundary conditions, suppose I have defined like it's a two-dimensional problem. So in one direction there is a counter like I, in another direction there is a counter like J. So like I told you that APTP is equal to AT plus AWTW. So for the similar kind of grid points, like from 1 to 10, if you have a same type of situation, like I've shown you that in the case of in when I described the Gauss-Seidel method, I told you that there's some equation that you will get, and all the equations are of the same nature. So you can form the loop, and then with that loop, you will have that you will get the value of temperature, like APTP is equal to AT plus AWTW upon something. So you will write something like this. With depending upon the boundary conditions, then you will form the loops, and finally, when this loop will get solved, it will get terminated, and finally you will get the value of temperature at every point, at all the 25 points. So this is actually I found the angular direction code. Code in the angular, in the cylindrical coordinates. I'm not getting the code in the Cartesian coordinates right now. So in this way, you will use any platform. You can choose any platform, like you can choose the C++ or C platform. Here I choose the MATLAB platform to find the solution of the variable temperature.
Okay, sir.
So any questions, ma'am?
So, sir, as of now, we do not have any further questions. But
Okay.
as I said earlier, if there are any questions from any participants, I'll forward them to you.
Okay, yeah.
And I would like to thank you from Mechanical Engineering Department, A.D. Patel Institute of Technology, Constituent College of CVM University. And I really appreciate the way you have formulated the approach, and you have narrowed down things as you have talked about conduction and convection. So the amount of ultimate of the topic, and you have summarized it in such a beautiful way. Thank you so much, sir.
Thank you very much. Thank you for inviting me and giving me the opportunity to present here. And I'm also thankful to all the participants who patiently listened my presentation. Thank you very much.
Okay, sir. Have a nice.
So shall I leave now?
Yes, sir. Thank you.
Thank you.